Hi everyone, it's Mr. Thompson. In this video we're going to talk about ionic and covalent compounds. In chapter 4 we've talked a lot about chemical changes, and all chemical changes or chemical reactions involve breaking bonds and making new bonds. And there's two major types of bonds in chemistry. The first are ionic bonds and the second are covalent bonds. Ionic bonds occur only between metals and nonmetals, and those are going to involve a transfer of electrons. In that case, the metals will transfer one or more electrons to the nonmetals. A covalent bond is different. Electrons aren't transferred. The atoms overlap and they sort of share the electrons, and you might have heard that term before. Sharing's in quotes because it's a little bit misleading. A more accurate way to describe it would be that the electrons sort of tolerate each other. They're really after the nucleus of the other atoms, so they don't really want to be next to each other, but they sort of put up with each other to try to get closer to the other nucleus. We're going to talk more about that in some future chapters. And just so you know, what I call a covalent bond, your textbook also calls a molecular bond. So the first question to determine what type of bond is taking place is to know the difference between a metal and a nonmetal. So the key is to use your periodic table. And your periodic table has a stairway. I'm going to show you a picture of that in a minute. But to the left of the stairway, you'll find the metals, and to the right of the stairway, you'll find the nonmetals. So this is a picture of the periodic table that you have on your pink reference sheet. And the stairway is a little bit difficult to see. I tried to put a bold line here, but it kind of zigzags across this area of the table. So anything to the right of that stairway is considered a nonmetal. And anything to the left is considered a metal. And most of the elements on the periodic table are metals, and that includes some of the radioactive metals down in this area here. Now there's some elements that touch the stairway that have properties of both metals and nonmetals, and we call those metalloids. So those are going to involve elements like boron, silicon, germanium, arsenic, antimony, tellurium, polonium. You can treat these as nonmetals for this chapter. We'll talk a little bit more about those properties later. So let's quickly practice just to make sure that everyone's up to speed. So I put 4 compounds here, and all you need to do is determine whether they're ionic or covalent. So it's very straightforward. Find each element, look at their location on the periodic table, and from there you should be able to figure this out. Remember that ionic compounds are made up of a metal paired with a nonmetal. Covalent compounds are made up of only nonmetals. So for question 1, it's carbon dioxide. Carbon's located here. Oxygen's located here. They're both nonmetals, so this would be a covalent compound. Electrons are not transferred between those two elements. Number 2 is TiO2. Ti is titanium, which is located here. We've already found oxygen. This is an example of an ionic compound. In this case, titanium is going to transfer electrons to the oxygen. Number 3, KBr. K is potassium, also a metal. Bromine over here is a nonmetal. So this would be ionic. Number 4, PCl3. Phosphorus is over here. That is a nonmetal. Cl, also on the right, a nonmetal, so this is a covalent compound. So now that you know the difference between the two, we're going to get into a little bit more detail about how to name them properly and how to write their formulas. So let's start with ionic compounds. First of all, ions are atoms that have either lost or gained electrons. They're like atoms with a charge. Metals tend to lose electrons, and they form positive ions. Those are known as cations. Nonmetals tend to gain electrons, and they form negative ions. Those are known as anions. This can get confusing, and you might think, well, if metals are losing electrons, how could they become positive? Well, remember that you're losing a negative charge. And by losing a negative charge, you become more positive. Okay, so negative minus a negative is equal to a positive. Your periodic table will tell you the charges of the common ions. I'm going to show you a picture of that in a minute. And we'll talk about why the ions have the charges that they do a little bit later in the semester. So here's another diagram of the periodic table. It's a little bit bigger. And what we've done here is put the most common ion charges at the top of each column. So all of the elements in group 1, when they form ions, will form +1 ions. That means that those substances will lose 1 electron, typically. All the elements in group 2 will form +2 ions. Those will lose 2 electrons. When we get into the middle, I'm sorry, you'll also see in the top right corner of every box, we put the charges as well. When you get into the middle of the periodic table, you'll notice that elements have multiple charges. So vanadium is a good example. Vanadium can lose 2, 4, 3, or 5 electrons, and it just depends on the situation. So for now, we're going to skip this area of the periodic table. These are the transition metals. They tend to break rules, so we'll save those for a different chapter. So we're going to focus on the main group elements, group 1, group 2, and then we'll come over to group 13, and the elements in group 13 all form +3 ions. They lose 3 electrons. Group 14 is sort of in the middle of the range, and it's actually difficult to lose 4 electrons. It's also difficult to gain 4 electrons. So these elements tend to not form ions until you get down to the very bottom, like tin and lead. Once we get over that hump, then we start to get into the elements that gain electrons, and that would be group 15, group 16, group 17. And those are going to gain either 3 electrons for group 15, 2 electrons for group 16, 1 electron for group 17. Group 18, they do not form ions. These are called the noble gases. And they're pretty stable. They don't really need any electrons, and they don't need to get rid of any electrons. So they tend to not react with many things at all. So for this chapter, we're going to tell you what the ions are. Later on, we'll explain why the elements in group 1 all form a +1 charge, and why the elements in group 2 all form a +2 charge. But because we're just introducing the concept, you need to trust us on this. And once we learn the formulas and learn how to name the compounds, we'll go back into a little bit more detail. Ions don't exist on their own. They have to bond, and they form ionic compounds. And the formula of the compounds is going to depend on the charges of the ions involved. For ionic compounds, there's only one valid combination. So for example, sodium and chlorine can only combine in one specific way. And the goal is to find a ratio that results in an overall charge of 0. So all ionic compounds are neutral, and your job is to figure out what's the magic ratio to get the charges to add up to 0. The rules for naming compounds are pretty straightforward. These are all made up of 2 substances. The first element, you're just going to name it, and it's always the metal. So again, sodium is a good example. The second element will be a nonmetal, and we're going to drop off the ending and add IDE instead. And the subscripts will not affect the name. So here's a few examples. So the first one, NaCl. The first element is sodium. The second element is chlorine. So for the first element, we leave that name alone, and we just keep it as sodium. For the second element, which is chlorine, we take the ending, we drop that off, and we add IDE, and so it becomes sodium chloride. The second example, Ca is calcium. We leave that name the same. Second element is oxygen. So we drop off the ending and add IDE. Sometimes it's a little difficult to figure out where you drop the ending exactly. For example, it's not oxygenide or oxygide, it's just oxide. You'll learn them pretty quickly. There's only a few that you need to worry about. The last example is MgF2. First element is magnesium. That name stays the same. The second element is fluorine, so we drop off the ending and it becomes fluoride. And notice that we don't do anything with that 2. We don't say magnesium difluoride or magnesium bifluoride. We just say the element names. We don't worry about the numbers. So let's practice a bit. Let's write some formulas now for some simple ionic compounds. Number 1, sodium chloride. We just did that, but it's worth just taking a look. The way you want to do this is to have your periodic table ready. We find sodium. We notice that it's in group 1, so it has a +1 charge. And we find chlorine. It's in group 17. It has a -1 charge. So the way I set these up at the beginning when I'm just learning this is, I write Na plus and Cl minus. I check my charges, and if I combine those in a 1-to-1 ratio, those charges will cancel. So my final formula is NaCl. For the second one, calcium chloride, we look up calcium. It's in group 2, so it has a +2 charge. Chloride we know is Cl with a -1 charge, and we tend not to write the 1. You can, it's totally fine, but chemists tend not to do that. So if I were to just put these together and write CaCl, I would be wrong, because 1 negative doesn't cancel out 2 positives. What I need to do is find a different ratio. It's going to take 2 chloride ions to balance out the +2 charge of the calcium. And the way we write that in the final formula is to put a subscript of 2. So CaCl2, it means there's 1 calcium and 2 chloride ions. And notice that the charges don't appear. So it's fine to write the charges at the beginning as you're trying to figure out the formula, but your final answer should have no charges because they cancel. Okay, number 3 is aluminum chloride. Aluminum is in group 13. It has a +3 charge. 1 chloride's not going to do it. 2 chlorides won't do it. It's going to take 3 chloride ions to balance out the +3 charge of the aluminum. So our final formula will be AlCl3. Last example, aluminum oxide. So we know aluminum is Al +3 or 3+. We'll find oxygen. Oxygen is in group 16. It has a -2 charge. So this is a little funky because one's +3 and one's -2, and you want to think about what's the least common multiple between those two numbers, and that would be 6. So I want to get the positive side and the negative side to both equal 6. That means it's going to take me 2 aluminums and 3 oxygens to get this to work, and so our ratio will be Al2O3. Once you get the hang of this, you're not going to need to draw it out like this, but I find at the beginning it really does help just to set it up this way. It's going to help you understand what those subscripts are all about. So next we're going to talk about covalent compounds. Covalent compounds involve only nonmetals, and because of that, ions aren't formed. So there's no electrons being transferred, and there aren't any charges on the atoms. Because of this, atoms can bond in a variety of different combinations. So if we picked 2 elements like nitrogen and oxygen, they can form multiple compounds. The examples I gave here, NO, NO2, N2O, N2O4, and there's a bunch of others. So because they're all different substances, we can't call them all nitrogen oxide. Just to give you a sense of the differences, NO2 is a brown gas. It's a major component of smog. N2O is a colorless gas. It's used in dentist's office and in race cars. It's nitrous oxide, otherwise known as laughing gas. So these couldn't be more different, and as a result, we need a different naming system. The solution that chemists came up with was to use prefixes. So these are a list of the first 10 prefixes that we use in chemistry, and these are also listed on your pink sheet, so you don't need to memorize them. Some of them should look familiar to you if you think about geometry. A hexagon has 6 sides, an octagon has 8 sides. The one that people tend to get tripped up on is number 4, which is tetra. But if you've ever played the game Tetris, which is the greatest video game ever invented, everything in Tetris is about the number 4. Every block that falls from the top of the screen has 4 little pieces. The goal is to always stack up 4 rows together to get the most points. So hopefully that'll help you remember that 4 is tetra. So the rules for naming covalent compounds go like this. The first element will get a prefix except mono. You never start the name of a compound with mono. The second element in the compound will always get a prefix no matter what. And just like we did with ionic compounds, we're going to use that IDE ending. So here's a couple of examples. NO. The way we'd name this is nitrogen monoxide. Notice that there's only one nitrogen here, but we don't start the name of the compound with mono. There's one oxygen, but we do give that a prefix, and we have that same IDE ending. NO2 would be nitrogen dioxide. N2O would be dinitrogen monoxide, and notice here that we do have a prefix for the first element because it's not mono. And then finally, N2O4 would be dinitrogen tetraoxide. I never know quite what to do with this. I think some people might just put those together and call it tetroxide, but I tend to write out both vowels because I think it sounds better. When you write formulas for covalent compounds, my best advice is don't think about it. Don't worry about the charges, just do what the prefixes tell you. So for example, carbon monoxide would be CO. 1 carbon, 1 oxygen. Carbon dioxide, CO2. And then dihydrogen monoxide, this is a substance you've probably heard of before under a different name. Dihydrogen refers to 2 hydrogens, monoxide, 1 oxygen. So H2O, otherwise known as water. So let's try some. Let's try to review everything we've learned and see if we can put everything into practice. So the goal here for these 2 practice problems is to write the correct formula. So the first thing we want to do is identify what kind of substance it is. Is it ionic or covalent? Because they follow different rules. So use the periodic table. We find sulfur. Sulfur's to the right of the stairway, so it's a nonmetal. Fluoride is based on the element fluorine, which is also a nonmetal. So this is a covalent compound. Another giveaway is the prefix, hexa. You would never use a prefix with an ionic compound. So my best advice, as I said before, is don't think, just do. So sulfur is S, fluoride is F, and the hexa refers to the number 6. So the formula is SF6. Don't worry about charges because there are no charges here. I know that might be confusing. If you look at the periodic table, you might say, well, sulfur has a -2 charge, fluorine has a -1 charge. Those are both negative. They're not going to attract one another. How does that form? Well, there aren't any charges. There are no electrons being transferred. The charges that I drew here are for ionic compounds only, and this is not an ionic compound. The second example is calcium fluoride. So we'll find calcium. It's in group 2. It has a +2 charge. And actually, before we even get there, so calcium is a metal. Fluorine is a nonmetal, so we have to make sure we specify that this is an ionic compound. It's a metal plus a nonmetal. So because of that, I need to know the charge on the calcium. It's +2. And the charge on the fluorine, or the fluoride, is -1. And my goal here is to build a compound where the charges add up to 0. And right now, these do not add up to 0. I'm going to need to add a second fluoride. Now I have +2 and -2, so the way we write the final formula is CaF2. And notice that it doesn't say difluoride here. It just says calcium fluoride because there's only one way to combine those 2 ions, and it's CaF2. Last slide, we're going to try to name some compounds now. Let's follow the same procedure. So first step, let's identify what kind of a compound it is. This is Sr3P2. So we'll find strontium right here. It's a metal. P is phosphorus. That is a nonmetal. So metal plus nonmetal means we have an ionic compound. The rules for ionic compounds are that we write the metal name first, and we write the nonmetal second, and we drop the ending to replace it with IDE. So phosphorus becomes phosphide. And that's it. The name of this compound is strontium phosphide. Notice that we didn't do anything with the subscripts. They don't factor in at all. If you were to call this tri-strontium diphosphide, it would be wrong, because ionic compounds don't need prefixes. Number 2, P2O5, so we know that phosphorus is a nonmetal. We also know that oxygen is a nonmetal, so this is a covalent compound. The rules for covalent compounds is that we need to use prefixes. This is a 2, so we're going to start this with di, and we write the full element name, so it's diphosphorus. Diphosphorus, and then 5, the prefix is penta, so it's pentaoxide. Don't forget that IDE ending. Diphosphorus pentaoxide. Now notice I picked these two examples on purpose. In the first compound, the phosphorus was second in the formula, and so it got the IDE ending. In the second compound, it showed up first, and in that case, you write the full name. So you would not call this diphosphide pentaoxide. The first element, you write the full name. The second element is the only one that gets that IDE ending. Hopefully this gave you a good overview of the difference between ionic compounds and covalent compounds, and you have a better sense of how to name compounds and write formulas. Your next step is to go through your packet and try the practice worksheets. And if you have any questions, please talk to me in class or stop by after school.